except for the cat. We don't have anybody um, to disturb, basically. So, everyone's sleeping at home. And I'm gonna go over, what was it? I think statistics, because this is the biggest. This is 44 slides here, right? So, yeah, we went over this slide yesterday. But let's go over it again. The field of statistics provides techniques for collecting, analyzing, and gaining insights from data. Data science relies on statistics to make data-driven decisions and solve problems. For example, a data scientist uses statistical models to predict sales based on possible marketing strategies. Statistical techniques are used throughout the data science lifecycle, so probability is the foundation of inferential statistics. Understanding the statistical techniques of a data science project ensures results are appropriately interpreted and communicated. So the basics of statistics. Oh, what, bruh? I just read this. Okay. So, range, mean, and standard deviation are the statistical measures. Correlation statistics is used in machine learning for better understanding data to create models. So this is an example here. We have just like different data structures. We have the collection, we have descriptive statistics, which here is the observed difference in aggressive and non-aggressive sort of behaviors in dogs. And then, because it's a graph, right? So that's descriptive. Inferential statistics is the observed difference, the test statistic, and the p-value. So the conclusion is association, not causation. Right, so this is the few types of data we have. We have categorical and numerical. Categorical is the one that's nominal and ordinal, and numerical is one that's discrete and continuous, which makes sense, right? Because continuous and discrete is how you structure numbers, right? You have continuous numbers and you have discrete numbers. Nominal and ordinal are types of categorical data. My stomach hurts for some reason. I don't know why. Welcome to the stream. Hello. Good morning, everyone. Today we're going over statistics. Right here we have statistics, chapter 5, 44 slides, right? So categorical data is representing categories or classes, i.e. gender, color, right? These things can't be measured in numbers. So the nominal data is a classification of categorical variables that don't provide quantitative data. Like I mentioned, it can't be in numbers, right? It's not quantitative. So for example, gender or color has no significance. Ordinal data is the type of data in which values follow a natural order, such as rating a product or service as excellent, good, average, or bad. So I guess ordinal you could make it into numbers like 5-star, 4-star, but there's like an order to it, right? It's not like 1.2 or something. 1.2 stars. But anyways, discrete data and continuous data are the ones that can be in numbers, represented like rain levels, humidity, etc. Okay, and then discrete data is the type of data that can only take certain values, such as number, i.e., number of people in a group. So it has to take a certain value. Like you can't not give it a value, right? And continuous data can have almost any numeric value. So, okay, so I guess discrete data is one that's like integers, right? And continuous data is one that is like a floating number. Okay, so types of statistics, we have descriptive statistics. It describes the data, and it is data analysis. Inferential data statistics, you get inference about the data to make prediction and data science. So descriptive statistics provides ways to explore the observed data through visualizations and numerical summaries. Let me repeat that again. So descriptive statistics provide ways to explore the observed data through visualization. So descriptive is visual. right? Like that graph from the earlier example. And inferential statistics is like modeling and estimation allow for conclusions to be drawn about the population from the observed sample of data. Alright, so descriptive statistics describe the basic features of the data in a study. They provide simple summaries about the sample and the measures. House price prediction. Important measures of descriptive statistics, measures of central tendencies, mean, median, and mode, measure of variability, range, standard deviation, and variance. So this is all the house prices, I assume. We have the count, we have the mean, the standard deviation, the minimum, the 25, 50, and 75 percentile, and then the maximum. So sampling. A common data science project goal is to analyze data to understand a population. Sampling methods are used to efficiently and effectively collect data and reduce bias, right? So these different methods exist so that we don't have like a skewed or like a unfair collection of data, right? So a population is the entire set of all individuals, items, or event of interest. An observational unit is an individual item or event of the population on which data can be recorded. Because constraints on resources can make obtaining data on this entire population impractical, many projects use data from a sample. So that makes sense, right? Like, how are you going to calculate the death rate or like the birth rate of the entire world if you can't count how many people there are? It's impossible to count how many people there are. So that's why you have to use sampling, right? So sample is the subset of observational units from the population from which data will be collected. The number of observational units in the sample is denoted by n. I don't know why, but n is just sample letter. So sampling and statistical studies. So what are the three statistical studies? There's sample study, observational study, and experimental study. So sample study, what is that? A study which is carried out on a sample which represents the total population. Observational study is a study where we simply collect and analyze data, no changes involved, right? We just study, collect, and analyze the data. But this is to represent a total population. And then the experimental study is a study in which conditions are controlled, manipulated by the experimenter. So, no, sample study describes World Health. I don't know why I read that as World Health Organization. I thought it was like who I'm studying. So you're just sample versus whole population, right? And the observational study describes how I'm studying them. So observe versus experiment. Hey Junie, it's so nice seeing you again. Oh my gosh, you make my day, bro. Statistical studies. So we have the observational study here. This is how we're studying, right? Remember right here, observational study is how I'm studying them. Observe versus experiment. So like these are how, and then the experiment, well, it didn't say like for the experiment, it just said like who and how versus from sampling versus observational, but not experiment. But anyways, let's see here. This is how we're studying them. We're studying them based on association, because these cards are not like distinct, they're just numbered, and we're just, I don't know. Anyways, I'm trying to make sense of this, but I don't know. So the experiment is causation. So average age is 10.6 years on the highway, and then city is 10.2 years. Causation, so you'd see on the highways the numbers are higher for miles per gallon. So if you take the highway, the miles per gallons are higher. And then yeah, that's the experiment. So sampling methods. sampling method is a process by which observational units are selected from the population to be included in the sample. So common sampling methods include the following: random sampling, stratified sampling, and cluster sampling. So random is observational units are selected at random from the population, pretty straightforward, in which each subset of n units is equally likely. So in stratified sampling, the population is first divided into groups called strata based on meaningful feature, then observational units are selected from each stratum. The strata feature is typically related to the primary feature of interest in the study, and thus all strata are sampled from. In cluster sampling, the population is first divided into groups called clusters based on a feature, then a random sample of clusters is selected. So you first divide them into groups or into clusters based on a feature. Then a random sample of some clusters is selected. Sample of some clusters. So you're taking samples from the clusters, right? So you first divide them into clusters, right? Each one has their own group, and then you take a sample from each of those clusters. So the cluster feature is typically not related to primary features of interest in this study, and thus not all clusters are sampled from. Okay, so that makes sense. Like you're looking for features on primary features of interest when it comes to stratified sampling. And then for random sampling, it's just like random, completely random. And then cluster sampling, you first divide them into groups based on a feature, but not primary feature. It's not related to that. Okay? And then the other sampling methods are systematic sampling and convenient sampling. So whoever comes first come, first serve, that's convenient. So that makes sense. In systematic sampling, from a random selected starting point of the population, every kth observational unit is selected. Typically, the value of k is selected to be the population size divided by the desired sample size n. So the kth person, typically the value of k is selected to be the population size divided by the desired sample size. So if your population, let's say, is 100 and your sample size is like 5, then the kth is 100 divided by 5, and that's 20. So it's like pretty even. Okay, so that makes sense. Random sampling in Python. See which slide this is. 15. Nice, good pace. So random sampling in Python. Pandas.dataframe.sample, n equals none, fraction equals none, replace equals false, random state equals none. So returns, okay, so this line of code returns a random sample of items from a data frame. The parameters n or fraction specify the number or fraction of items to be returned in the sample. So the replace parameter specifies whether sampling is done with true or without false replacement. And then the random state parameter optionally sets the random number generator seed for reproducible sampling. So it's all none here, and then the replace is false. So all parameters have default values. So if you call pandas.dataframe.sample, it only returns one row by default. One row. So that's the default. One row is the default. Measure of central tendencies. A measure of central tendency is a value that represents the center point or typical value of a data set. It is a value that summarizes the data, i.e. a student's GPA. So the mean or arithmetic mean is the sum of the values divided by the number of value, median, mode. These are simple, blah, 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 blah. Mean, median, mode. Wait, yeah, no, I got this. Range, largest, smallest. Variance is the measure of how far each data point is placed from the mean. I know variance is a little harder to remember than mean, median, mode, and range. I don't know why that's like less gone over. Like all the other ones, like you go over in third grade and stuff. So note from Zybook on calculating variance. The equation to calculate the variance of a sample is the sum of the squared distances from the mean divided by n minus 1. Dividing by n minus 1 rather than divided by n gives a better estimate of the population variance from sample data. So why is it n minus 1? Because you need a better estimate of the population variance from sample data. So if this is a sample, then you do n minus 1. So you don't normally do n minus 1 if you're doing it based on the population, right? If it's from the population, I think it's that one. And then if it's on the sample, then it's n minus 1 on the bottom. Okay, so standard deviation is a square root of variance. So that means standard deviation squared is just the variance, right? So standard deviation looks at how a group of numbers are spread out from the mean. So there's no absolute threshold value that defines a standard deviation as large or small because it depends entirely on the context of your data. A standard deviation of 3 for stock price movements in dollars could be large for a $10 stock but small for a $1,000 stock. So statisticians often use the coefficient of variation, CV equals mean over standard deviation over the mean times 100% to get it into a percentage to get a standardized measure of dispersion relative to the mean. So a coefficient of variation of 5% or less typically indicates low variation, while the value of 15% might be considered high variation in many fields. Okay. Alright, so a standardized score, or a z-score, describes how many standard deviations and in which direction a value lies from the distribution's mean. The equation to find a value standardized score is deviation. So the z equals x minus... Hello, it's Bacon67. Welcome to the stream. Welcome to the chat. There isn't a single universal threshold for z-scores, but there are commonly used thresholds depending on the context. You should keep the camera a bit to the left so the camera can move this slide. Okay, there you go. Hopefully that helps. Sorry, I'm outside right now, so I don't wake anybody up. It's like pretty early in the morning. So, there you go. So there isn't a single universal I already read that. So for identifying outliers, values with z-score over 1.96 falls outside of 95% of the data, and then 2.58 is 99%, and then over 3 is definite outliers in many fields. Perfect. Nice. All right. So a z-score is, we went over that. Over here, let's look at this. This is a common z-score threshold on normal distribution. So this yellow line is 90%, and then this blue line is 95%. Wait, yeah, and then this red line, or orangish red line, is 99%, and then the purple is 99.7%. So one-tailed is 90%, two-tailed is 95%, and then 99% is two-tailed, and then 3 sigma rule for 99.7%. Okay. In class activity, the mean train for fair cost is all of them combined. So you'd have like 8 over here, 8 zeros, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So 24. Okay, so you're dividing total by 24. And then you add it all together. See, 3 or 2.5 plus 2.5 is 5, plus 3 is 8, plus 3.5 times 2 is 7. That's 15. Plus 4 times 3. 15 plus 12 is 27, plus 6 is 35, and then 35 plus 6.5 times 2 is 13, 35 plus 13 is 35 plus 48, plus 7 is 55, 65. 65 plus 17 is 82. 82 plus 20 is 102 divided by, what was it again? Well, it has to be, oh my gosh, the mean, wait, 85, right? So what was it? 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. 85 divided by 24. That's 4.54, right? So number one is 4.54. The median is, what is it? That was 24, right? So 24, middle has to be like 12. Let's see, this is 8, 9, 10, 11, 12. So that's 3.5. So 4.54, 3.5. Suppose the response of $8 was instead $18 for the modified data. The mean would be, well, it has to be greater than, right? Because you're increasing the sum. So it's greater than. And then suppose the response of $8 was instead 18 for the modified data. The median would be, 3.5? Let's see. 8 would be, instead of 8 would be 18, right? But that doesn't matter, so I think it'd be equal to. So let's see. All right, 4.54, 2.5, greater than, equal to. Nice. All right, so the range of the cost feature for respondent who were extremely dissatisfied. Cost feature for respondent who were dissatisfied. Wait, the range, so that'd be 25 minus 0 is 25. Is we're extremely dissatisfied. Is the equal to the range of the cost feature for respondent who are dissatisfied. So what would the range here be? It's still 25, right? We can see a little line here, right? And then 25 minus 0, I think it'd be equal to. And the variance of the cost feature for the respondent who was extremely dissatisfied is the variance cost. Wait, what was the variance again? I forgot. Variance, right? It was the measure of how far each data point is from the mean. So if your mean is like, let's say here or something, like, or here, if you're gonna balance it out, or like here, then how far is the variance, the data points? This one has a higher variance than this one because it's like, where does the word variance come from? It varies, right? It varies, but if it doesn't vary that much, it has to be closer together. So the higher variance is the one on top, right? So we're extremely dissatisfied is, this is extremely dissatisfied. I think the variance is greater than, so it's greater, greater than the variance of the one that's just, yeah. So yeah, it's greater than, and it's equal to. Nice. Okay, so the percentile and quantile. So percentiles divide data into 100 equal parts. The nth percentile is the value below which n% of observations fall. So percentile divide data into 100 equal parts. The nth percentile is the value below which n% of observations fall. So, for example, the 50th percentile is the median. So half the data falls below this value. So the 25th percentile means 25% of the data falls below this value. So 25th percentile is less than the 50th. Okay, and then 90th percentile means 90% of data falls below this value. So if you get like the highest score in an exam, then you would want the 100th percentile, right? Because you want the highest one. So quantiles are a more general term for dividing data into equal-sized groups. They can refer to any division of the data. So there's 4 parts, quartiles, like a quarter, and then 5 parts, quintiles, 10 parts deciles, 100 parts percentiles. That makes sense. So percentile and quantile. The first quartile is known as Q1, or the lower quartile, is the value of the 25th percentile. And then the second is QT, the median. Third is Q3, the upper quartile, the 75th. The interquartile range is a measure of dispersion in statistics. This range corresponds to the distance between the first quartile and the third quartile. So IQR equals Q3 minus Q1. Larger IQRs indicate that the data are more spread out. That makes sense because they're on opposite sides, right? And you have to, when you subtract them, if the difference is higher, then they're further apart. So percentiles, interpretations, and calculations. Let's see what. Okay, 28 out of 44. Little cat break, Pixie and Yuki. So let's see. There are multiple methods for calculating percentiles. 3 methods that analysts use to calculate percentiles when looking at the actual data values is in relatively small data sets are as follows. The smallest value that is greater than k% of the values, the smallest value that is greater than or equal to k, and the interpolated value between the two closest rings. I did not understand any of that, but let's see if they explain it. So the calculated percentiles, to calculate percentiles, first we need to rank our data set. So if you have 11 values, you rank them from 1 to 11 based on smallest to greatest. And then the first method is greater than. Let's find the value that is greater than 70% of the values, and there are 11 values. So what is the 70th? So I would say it's the 7th one, but if there's 11, 7 is less than 70%, right? But 0.7 times 11 is 7.7. So if you round it up, you get 8. And then now you pick the 9th rank value in the data set, which is 40. Because you're finding a value that is greater than. So it has to be the one that is rounded up and then outside of that one. So if you're rounding up, you don't choose the one that you rounded up to. You go to the one that is below that one, right? Or lower in rank than that one. So greater than or equal to, you just go on 8th, and then interpolated, it's you do n plus 1, where p is the percentile and n is the sample size. So interpolated is n plus 1. If the rank is step 1 is an integer, find the data value that corresponds to that rank and use it for the percentile. If the rank is not an integer, interpolated between the two closest observations. 8.4 falls between 8 and 9, which corresponds to the data values of 35 and 40. So take the difference between the two observations and multiply it by the fractional portion of the rank. So what is the fractional portion of the rank? 0.4? Why is that the fractional? I guess because 40 divided by 100. Or just 11 though. Let's see. 8.4. Okay, so if you're trying to find the 70th percentile of this thing here, then the 70th would be between 7 and 8 because it's 11. So between that, 22 and 35, you'd get, or instead of that, you're doing 11 values plus 1, because that's the formula here, and then you multiply it with 0.7, because that's the 70th percentile, and you get 8.4, and 8.4 here is between 8 and 9, and then the fractional percentage is 40 out of, it's just like 0.4, why is it 0.4 though? Why is it not 0.4, 0.1 or something? I don't know. Multiply it by the fractional portion of the rank. Or, let's just using this one's fractional portion. Sorry about that noise, but subtract it by 35, and then you get 2. What is 2 though? What is this? Is the percentile or what? So you take the lower ranked value in step 3 and add the value from step 4 to obtain the interpolated value for the percentile. Take the lower ranked value in step 3, 35, and add the value from step 4, just 2, so you get 37 to obtain the interpolated value. That's 37. Okay, so you do, if the rank is not an integer, interpolated values between the two closest observations. 8.4. So you take the less one, and then you subtract them, and then you multiply it by the fraction of the first one, I'm assuming, and you get 2. Or the rank is 4. Fractional portion of the rank. Okay. How is the fractional portion of the rank 0.4? I don't understand that part. Let's ask ChatGPT to explain. Because this might be on the exam. Alright, let me type this in. How did the fractional portion of the rank equal 0.4? Okay, so ChatGPT is working its magic right now. Let's give him some time to breathe, right? Where were we? We were... Okay. So the rank is 8.4, right? And then the decimal fraction part, the whole number part is 8. The decimal fraction part is 0.4. So how's... Oh, okay, so this is the fractional... Okay, bro, I was multiplying 40%... 40 by 10 or like something. I thought... Okay, so the fractional point is 0.4 here. And that's what you multiply by to get 2. Okay, I would not have guessed that. That's crazy. Okay, so if the rank is not an integer, the interpolated between the two closest observations, 8.4 falls between 8 and 9, which corresponds to the data values of 35 and 40. So Pn plus 1, that's how you find the rank. And then percentile is 70. Total is 11 plus 1 is 12, right? So 0.7 times 12 is 8.4. And the interpolated value between 8, that's 35. 35 times 0.4? No, 35 plus the difference. So that's 5 times 0.4. That's 2. So, yeah. That's interesting. That's very interesting. So the measure of position. Measures of position indicates where a value is located in a numerical features distribution. So measures of position indicate where a value is located in a numerical features distribution. Measures of position. So let's say the quantiles. Class activity number 3. We're almost there. We have 10 slides left. So consider the numerical summaries and dot plots below for the train fare cost for the subset of 24 respondents who did not have a driver's license and were extremely dissatisfied with the fare. Responses are rounded to the nearest $half in the dot plot. So the median cost, maybe you're not going outside, little kids. You guys cannot go outside. It's only for the cool kids. So, the median cost. What is the median cost? Well, we have 8 here, right? Wouldn't it be 3.5 again? Or... the first quartile, or 0.25 quantile, is 25. Maybe if you divide 24 by 4, you get 6. So the first quartile is 0. The third quartile is, if it's 24 and you divide by 4, you get 4 times 3. No. 24 divided by 4 is not 4. It's 6. 6 times 3 is 18. So the 18th one, right? This is 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So the third quartile is 8.5. So 8.5 is the third quartile. And then the first quartile is 0. So 8.5 minus 0 is 8.5 for the interquartile range. And the standardized score of the response at $10. How do you do the z-score again? We could go back up. What was... Did it show how to do the z-score? Was there like a z-score? Okay, so x minus the mean over the standard deviation. What is x though? Oh, wait, hold on. No answers yet. So x is 24, I'm assuming. 24 minus 4.54 would be 19.46 divided by 5.24, which is around 4, but it's less than that because, or higher than that, because 19 is smaller than 20. So something around there. What? So x is not 24. X is actually 10, right? What is x supposed to be in the standardized, in the z-score? That's crazy. Well, I got these right. I said 8.5, but I'm at 6.5. So yeah, I know these ones. So what is x in the z-score? What is x in the z-score? Let's ask ChatGPT again. What is x in the z-score formula? Oh, wait, it was not typing. Oh my gosh. What is the z-score, or the x in the z-score formula? Alright, so let's see here. The x in the z-score formula has to be, drumroll please, round of applause. X is the raw data value you're measuring. Individual data point. So you have to take that part out? Wait, where do you get 85 from? So 85 here, if the test score has a mean of 70 and the standard deviation of 10, your score is 85. Then the z-score, 85. So this is your score. You just take that from the data set, right? And then you take that and you subtract it by, what is it, the mean, and then you divide it by the standard deviation. So you get 15 over 10, and that's how you get 1.5. But I don't understand how you're supposed to know. Oh, okay, so this is how you're supposed to know. This is x. Okay. I don't know why I was thinking x is like the count. Alright, but this makes sense now. So the x is what the value they give you. So you don't have to find x. So 10 minus the mean right there and divided by the standard deviation is 1.04. That makes sense. That makes a lot of sense now. 36. We have 8 slides left. So the measure of shapes by Zabuk is a distribution Okay, symmetric, skewed, symmetry, kurtosis. Wait. So distribution is skewed if the distribution's value extends far. Two common measures of escape are skewed and kurtosis. Skewed is a measure of the amount and direction of skew or departure from the symmetry. Positive values indicate the distribution has an extended right tail. So the right tail is on this side. That's positive skew. It's positive skew. And then the negative skew is on the left side. Because it's negative if the graph trend line is positive. So that part is confusing. That part is a little bit tricky because you think like it's skewed in the direction that the trend line is going, but it's not. It's the opposite. There's my cat. He's looking at me. Another one. Okay, so kurtosis measures the combined effect of tail heaviness, extreme values, and peak sharpness in a distribution. So higher kurtosis equals heavier tail and sharper peak. So what is that? Like a U shape or like a slope shape? Let's see what's. I don't think they have pictures of kurtosis here, but it's nice to know that that is how a. What is it? If it's a positive trend line, then it has to be negative skew. Okay, yeah, negative, positive, zero skew. So different x's kurtosis. I don't understand what that means, but a positive value for the kurtosis indicates a distribution more peak than normal. In contrast, a negative kurtosis indicates a shape flatter than normal. Analogous to the skewness, the general guidelines is that if the kurtosis is greater than 3, the distribution is too peaked. Too peaked. Too blah 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 blah. So correlation. Correlation is a statistical measure that expresses the extent to which two variables are linearly related. A correlation could be positive, meaning both values move in the same direction, or negative, meaning when one variable's value increases, the other variable's values decrease. So the positive correlation is both of them are going in the same direction. The negative correlation is that there's no relationship in the change of the variables. Negative correlation. So or neutral correlation, sorry, there's nothing there. And negative correlation is that it goes in the negative direction. Correlation between a variable, however, does not automatically mean that the change in one variable is the cause of the change in the variable of the other. So the causation indicates that one event is a result of the occurrence of the other event, i.e. there's a causal relationship between the two events that is also referred to a cause and effect. Theoretically, the difference between the two types of relationships are easy to identify. An action of occurrence can cause another. For example, smoking causes an increase in the risk of developing lung cancer, or it can correlate with another. For example, smoking is correlated with alcoholism, but it does not cause alcoholism. In practice, however, it remains difficult to clearly establish cause and effect compared with establishing correlation. So the Simpson paradox occurs when groups of data show one particular trend, but this trend is reversed when the groups are combined together. So, for example, you and a friend each do problems over a weekend. Your friend answers a higher portion correctly than you on each of 2 days. Does that mean your friend has answered a higher proportion correctly than you when the 2 days are combined? Not necessarily, because look at this. You have a higher score or they have a higher score on day 1, but you have a higher score in the end because they were graded differently. That makes sense? Hypothesis testing. Hypothesis is an assumption made based on observations of an experiment, i.e. geocentric versus heliocentric theories. Hypothesis testing is a method used to test whether the assumptions made are plausible or not, i.e. which COVID-19 vaccine is more effective, mRNA versus weakened virus. Type 1 error, reject HO when HO is true. You don't believe in your homegirl, but then you don't reject her, but you should leave her. So that's a type 2 error. So type 1 is being treating your girl bad, and then type 2 is not leaving her when you should. So null hypothesis is commonly accepted fact. Alternative hypothesis is an opposite to the null hypothesis, and it challenges the null hypothesis. So we did all this. I don't know why I'm going up. Let's see. Okay, 43. So we don't need the summary, but this is the last slide so far. Look at this. Look at this cutie guy. Look at this. Look at this. Oh dear. Oh yeah. Get that. Scratching. Yeah. Oh dear. Hi. Okay. So hypothesis testing, null hypothesis, and alternate. Oh baby. Baby. Oh. Cure rate of at least 65% for people over 65 with COVID-19 state that the null and alternative hypotheses describe both type 1 and type 2 errors in context. The false positive is rejecting HO when you shouldn't. So the researcher believes that the vaccine is less than 85% when it is at least 65% or more effective. So you're believing the opposite, the alternative hypothesis, when you shouldn't. That's the false positive, right? That's the type 1 error. Type 2 error is a false negative when you shouldn't reject the null hypothesis, but you do anyway. Or you should, but you don't. So that makes sense. So we're done with the statistics one, the statistics slides. That was the biggest of them all, right? So we have 2 more slides left. We have data ethics and linear algebra. Let's see here what linear algebra is about. It's 33 slides. Let's see, data ethics is 23 slides. Data ethics seems easier, so I think I'll do linear algebra first, just to get that out of the way, you know? Just gotta get it out of the way. What does he want? He wants to come out here? Oh, baby, baby, baby. I guess we gotta let him out. That's my boy. That's my study buddy. Okay. Linear algebra is the branch of mathematics that deals with vector spaces. There are 3 distinct but related ideas of vectors: physics perspective, computer science perspective, and mathematics perspective. He doesn't like the hammock. Okay, sorry about that. Let's see. So vectors are arrows pointing in space. A vector is defined by its length and direction, can be moved around the space and be the same as long as 2 factors are not changed. What are those 2 factors? They're not gonna say. Or the 2 factors are the length and direction. Look at this sneaky little girly. I actually don't have time for this. I ain't got time for this. It was nice while he was out here, but I can't let the door be open and the other cats go because I'm on a time crunch here, right? I could have slept this morning, but I didn't. So their vectors are ordered numbers, ordered list of numbers. In the computer science perspective, it has to be ordered. Mathematics perspective, generalized with previous perspective, both of them. So it's added, it can be multiplied by a scalar, and it requires a semester-long course, but let's do what's only required here. So vectors. Abstractly, vectors are objects that can be added together to form new vectors and that can be multiplied by scalars, i.e. numbers, also to form new vectors. Vectors are points in some finite dimensional space and are useful ways to represent numerical. A list of 3 numbers corresponding to a vector in 3-dimensional space and vice versa. For example, the 3-dimensional vectors height, age, and weight. In Python, lists aren't vectors and hence provide no facilities for vector arithmetic. So we use type alias to define vector as a list of floats. So from typing import list, vector equals list of float. So lists aren't vectors, so I have to make it float. Height, age, weight, 70. Where are my viewers at though? Where are my viewers at? So vector creation with numpy is import numpy as np.array. And then the grades are as such. Adding vectors. For example, you get that. Adding vectors over here, you import numpy as np defining add v1 plus v2 sum equals v1 plus v2 return sum v1 equals np.array np.random rand int 1 to 10 size equals 5 generate 5 integers between 1 and 10 np.array np.random.rand int size 5 generates 5 integers between 10 and 20. So the result is that you add these two and then you print the results. So multiplying a vector by a scalar. Between 0 and 1 is squished. Less than 0 is reversed. Greater than 1 is stretched. That makes sense. So np.array is your vector, right? So the scalar product is np.multiply. That's the function that you use on NumPy to multiply a vector by a scalar. So that's the result. Right? So part A, define a method to calculate v1 plus v2 minus v3 and then store and print the results. So the v1 and v2 and v3 are those. And then you define a method to calculate it. That is using addition between the vectors. Why do you subtract it? So that's just those 1 character strings that you put in between each of those vector values, right? And then in the end, that's your result, right? But you put the result based on A, B, and C for A, B, and C in zip v1, v2, and v3. So v3 is basically, what is zip? I don't know. I don't know what zip is. Like, how do you know what zip is? How do you know zip is subtracting and adding A, B, and C? So you print the float. Okay, so that's the answer. I thought this thing was the answer, but it's not. So yeah. Print component wise means mean of v1, v2, and v3 equals apostrophe. So plt.quiver 10 of 22. We have 12 more slides to go. I would take a break, but I don't want to end the stream here and then start again. But we do have data ethics to go over as well. I think that's easier than the other one, this one. Because this is taking a lot of brain power. Let me see. 10. Alright, so let's just focus on the code of linear algebra because I already took linear algebra class. So import matplotlib.py plot as plt, plt.quiver gives you the origin at 0, 0, and then 4, 3 for 0.1, right? And then so you have to do point show in the end to get a graph. It won't work otherwise. And x limitation, y limitation is the graph parameters, basically. And then the quiver is the points, right? And magnitude, we know what that is. It's just the square root of each value of the vector being squared. The code is import numpy as np. Then you have your vector there, right? np.array. And the magnitude would be this np.square root of the sum, right? So magnitude of vector without norm module. Magnitude of the vector. And then you print whatever that is, that string there, and then np.linalg.norm of vector 1. Linalg.norm is how you get the magnitude. Linear algebra norm module gives you the same value as doing np.square root of the sum of vectors 1 times, or 1 to the power of 2. So vector dot products, we know that v times w, vw cosine theta, vectors dot products in class activity. Write a method to calculate the dot product of the two following vectors. So I'd say vector 1 just times vector 2, adding it together. np dot. Is that the answer? Okay, so I guess that's the answer. np.dot is a function that you use to do the dot product. You don't even have to multiply by 2 and then get the answer, or by each other and get the sum of that. Just do point dot. And then the cross products, pretty simple. Projection is magnitude squared. That's the hard part of the projection, right? Because you forget. Okay, also the subscript of projection is the denominator, and the top and the one that you're calculating on the side as well. So that may be small, but he has big dreams. Small cat, big dreams. So slide 16, we got 4, 5, 6 more to go. 6 more slides. My head hurts, but let's keep going. So write a Python code to find the projection of v1 and v2. So you have the two vectors, right? v1 and v2. Import numpy as np. And the magnitude of the array is np.linalg.norm, right? So that's what we went over before. That's pretty straightforward. You put that on the bottom, but you also have to square it. So put that on the bottom, square it. Multiply it with a vector 2. Y, what is vector 2 here? Is b. Vector 2 is b. And then the NP is the dot product of the beginning. And that's your answer. So matrices is a two-dimensional thing. It's hard to continue with this. 17. I think I'll just go to data ethics now. I've been studying for 1 hour straight. I might need to eat and then come back.